Right now, as you watch this, you're caught in the middle of the universe's greatest feud. The forces holding your atoms together follow completely different rules than the gravity keeping you in your chair. And this cosmic rebellion might be the key to everything, or prove that everything is impossible to know. For over a century, physicists have hunted Einstein's holy grail, a single unified field theory that explains all of reality. We've already proven it's possible. We unified electricity and magnetism, merged space and time. But gravity refuses to play nice with quantum mechanics, like two master painters working on the same canvas in completely different languages. If we crack this theory of everything, we unlock black holes, the universe's birth, and the deepest question of all, is reality just mathematics wearing a disguise? The string theory revolution once promised answers, but quantum gravity keeps slipping through our fingers. Picture Einstein's world. Smooth, elegant, predictable. Gravity isn't a force, it's space-time itself curving around massive objects. Drop a ball, and it's simply following the straightest path through curved space. General relativity gave us GPS satellites and black hole predictions that proved flawlessly accurate. Now enter quantum mechanics, a realm where particles exist in multiple places simultaneously, where the act of observation changes reality, where probability rules everything. It's chaotic, unsettling, and completely alien to our everyday experience. Yet it powers every computer chip and laser in existence. These two theories are like feuding siblings, each perfect in its own domain, but the moment they meet at a black hole's heart or the universe's birth, they start screaming mathematical nonsense. Have you ever wondered why the universe seems to follow different rules at different scales? Enter the gladiators of physics, each wielding their own weapon against the mystery. String theory. Edward Witten and Michio Kaku's cosmic symphony. Everything you see, every force you feel is actually tiny vibrating strings smaller than atoms. Different vibrations create different particles, like musical notes creating different sounds. These strings dance in 11 dimensions we can't perceive, weaving reality itself. The string theory hypothesis promises to unify all forces under one mathematical framework. It even sparked a wave of optimism in the 1980s that the final answer was within reach. But here's the catch. It requires dimensions we can't see and makes predictions we can't yet test. It's mathematically beautiful but experimentally elusive. But Lee Smolin and Carlo Rovelli say, forget the strings. Their loop, quantum gravity, treats space itself as granular, made of discrete loops smaller than atoms. Instead of smooth space-time, reality becomes pixelated at the smallest scales. This quantum gravity approach doesn't need extra dimensions. It directly tackles the problem by quantizing space and time themselves. When you zoom in far enough, space-time becomes choppy, like discovering that what appears to be a smooth photograph is actually made of pixels. Meanwhile, researchers like Erik Verlinde propose something radical: emergent gravity. Maybe gravity isn't fundamental at all, but emerges from deeper thermodynamic principles, like temperature emerging from molecular motion. It's a complete paradigm shift, gravity as an illusion hiding something deeper. These aren't just competing theories. They're completely different visions of reality's foundation. Here's where dreams meet cold reality. The Large Hadron Collider at CERN, humanity's most powerful microscope, found the Higgs boson in 2012, completing our standard model, the best map we have of particles and forces. But it also delivered a crushing blow. No supersymmetric particles. Partner particles string theory needs to balance its math. No extra dimensions, no smoking gun for string theory. LIGO detected gravitational waves in 2015, proving Einstein's space-time predictions and opening a new window into the cosmos. These ripples from colliding black holes confirmed general relativity beautifully, but left quantum gravity a complete mystery. The Planck satellite mapped the universe's baby picture with unprecedented precision, showing us the cosmic microwave background. Yet these triumphs only deepened the mystery, confirming what we knew while revealing how much we don't. Each experiment validates pieces of our understanding while the unified field theory remains frustratingly out of reach. What happens to science when our most advanced instruments can't detect what our brightest minds believe? But here's the truly unsettling possibility. Roger Penrose and other critics argue that maybe no theory of everything is possible. Perhaps reality is too complex, too fundamentally mysterious for any human framework to capture. This raises the ultimate question. Is reality written in mathematics, or are we just projecting our tools onto a cosmic mystery? Stephen Hawking believed that discovering a complete theory would be the ultimate triumph of human reason, a moment where we'd not only understand the universe, but glimpse the mind of God. To him, unifying gravity and quantum mechanics wasn't just a scientific task, it was humanity's grandest question. If we found a theory of everything, would we understand reality or just have a very sophisticated description of it? The holographic principle, famously explored through Juan Maldacena's ADS-CFT correspondence, suggests something even more radical, that our 3D reality might be information encoded on a 2D surface, like shadows on a cave wall. Reality itself might be a projection, and the theory of everything might not be describing fundamental particles and forces, but the information patterns that create the illusion of our world. Right now, at Princeton's Institute for Advanced Study, Nima Arkani-Hamed is exploring how space and time might emerge from quantum information patterns, treating space-time not as fundamental, but as something that crystallizes from deeper quantum relationships. Meanwhile, researchers are developing new mathematical frameworks that might bypass traditional approaches entirely. We're not just looking for new theories, we're questioning whether space, time, and matter are even the right starting points. The revolution might not be in the answers, but in asking completely different questions. So here we stand, cosmic detectives armed with mathematics and intuition, chasing the ultimate mystery. We've split atoms and mapped galaxies, unified forces and bent space-time, yet the deepest question remains. Why does the universe seem designed for minds that can ask such questions? Maybe the theory of everything isn't just about unifying forces. Maybe it's about understanding why reality built itself to be understood. In seeking to explain everything, we might discover that we are the universe's way of knowing itself. The symphony of strings continues playing, the loops of quantum gravity keep dancing, and somewhere in the mathematics, reality guards its deepest secrets. The theory of everything remains just beyond our grasp, tantalizingly close, eternally mysterious, and absolutely worth the chase. Whether through string theory's elegant mathematics, loop quantum gravity's pixelated spacetime, or some revolutionary approach we haven't imagined yet, the quest continues. And perhaps that's the point, not to find the final answer, but to keep asking the most beautiful questions reality has to offer. If this cosmic mystery sparked something in your mind, subscribe to dive deeper into the universe's greatest puzzles. This is Theory Spark. Next up, what's the true nature of time? The rabbit hole goes deeper than you think.